A lot of mathematics is about finding generalizations and patterns. And in fact, for many common distributions, if we can show that they satisfy a few simple properties, there is a general framework for fitting that distribution response types through generalized linear models. And that's if these distributions belong to the exponential family. So if I'll start with just a single parameter distribution, say the distribution depends on one parameter theta. The distribution belongs to the exponential family if its probability density for continuous or probability mass for discrete function can be written in this form. What I've written f of x is a function that depends on the variable x, a of x, multiplied by a function that doesn't depend on x but does depend on the parameter theta, multiplied by the exponential of c of theta times d of x. So the critical things here are that we need the range of x not to depend on theta. It's easy to overlook that one. But notice here that all of the functions, the a function, b function, c function, and d function, depend on either the variable x or the parameter theta, but never both. So I can separate the function out this way. And we do actually have both a multivariate extension of this and a multi-parameter extension of this. So it's the same idea, but instead of having a parameter theta, I've got a vector parameter theta consisting of theta 1, theta 2, up to potentially theta n, and I would just then take the dot product with a vector function of my response, x. So when I say many distributions meet this criterion, I think you'll be familiar with most of these will be ones you've seen before: a normal variable, a geometric variable, an exponential Poisson, and so on. Some of them, particularly those with more than one parameter, may or may not be in the exponential family. A binomial, if I know the number of trials but I don't know p, it's in the exponential family. If I'm trying to describe n as well, the number of trials, then the range of the variable depends on the parameter, so it's not in the exponential family. And the same reason for the negative binomial. So some of these are super easy to show that they can be written in this form of a function of the variable times a function of the parameter multiplied by the exponential of a function of the variable times a function of the parameter. There's also some there where it looks like I can write it in that form, but in fact the range of the variable would depend on one or more of the parameters. So for example, the Pareto variable, if I don't know m and alpha, it's not in the exponential family because the range of the Pareto variable is m to infinity. I could actually say the Pareto's in the exponential family if I know m and I'm still trying to obtain information about alpha. What does this look like? How do I show something is in the exponential family? So I'll start with a case here of a binomial variable where n is known. So critically, x doesn't depend, the range of x, doesn't depend on the unknown parameter p. If I write the probability mass function here, that the probability that x takes a value little x is n factorial over x factorial n minus x factorial, p to the x, 1 minus p to the n minus x. So the first things first, the range of x is just 0, 1, 2, 3, 4 up to n. Doesn't depend on p, so it hasn't failed to be in the exponential family on that criterion. So what I need to do now is write this as a function which contains x but not p times a function that contains p but not x multiplied by e to the function that depends on x but not p, multiplied by a function that depends on p but not x. If I just rearrange this, all I've done is I have pulled through a factor of 1 minus p to the minus x. And so now you can see I've left the factorial terms at the front. I've got the 1 minus p to the n. And all I've done now is I've taken the exponential and the logarithm. So I haven't changed the value of p over 1 minus p to the x to rewrite that as the exponential of x log p over 1 minus p. If you just excuse me with some bad typesetting, that's the same as the statement written above. I've just put some very ugly spacing in there. The reason I've done that is that I can then sort of throw brackets around these or squares around these. They're rectangles, not squares, but who's counting? Anyway, so you can see that the first term, the one in the solid blue box, depends on x but not p. The one in the solid red box depends on p but not x. Dotted blue depends on x but not p. Dotted red depends on p but not x. Remember, n is known, it's just a number, whatever it happens to be. So if I write this as a function that depends on x but not p times a function that depends on p but not x, and so on, well, excuse me slightly having the terms in the exponential in the other order. But if we correspond the boxes, you can see I've got an a of x, I've got a b of p, I've got a c of p, and I've got a d of x. So there's no term in there where I've got a function of p and x. Now, when we wrote the binomial probability mass to show it was in the exponential family, there's actually multiple ways that I can do that. I can write a distribution in the form of the exponential family more than one way. But there is a form that we call the canonical form, or sometimes the standard form. And we obtain this by, when I've written it in this form, where I've separated a function of the variable multiplied by a function of the parameter times the exponential of a function of the parameter times the function of the variable. Once I've got it in that form, I don't deal with the parameter theta. I instead deal with c of theta as a new parameter, as the natural parameter for that distribution. So effectively means I don't think of theta anymore. I think of some function of theta as the parameter. What I can do then, well, whatever c of theta is, I just call that c. It doesn't affect a of x or d of x because they don't depend on theta. But obviously, b of theta, if theta doesn't exist anymore, b is a function of the natural parameter now, c. And for example, what it would mean is that for the binomial variable, where I know the number of trials, instead of saying I know n, I want to parameterize based on p, I could say I want to parameterize based on the log odds ratio, or log of p over 1 minus p, since this is the natural parameter. And just one more example of this, if I have a Poisson variable with rate parameter lambda, then I can write its probability mass function. Definitely the range of this doesn't depend on the rate parameter, so it could be in the exponential family. And indeed, I can show it is by writing it in this form. 1 on q factorial, that's a function of the variable but not the parameter, multiplied by e to the minus lambda, that's a function of the parameter but not the variable, multiplied by e to the q log z. Obviously, q is a function of q, and not log z, log lambda. Log lambda is a function of the parameter. And more than that, the function of the parameter inside the exponential term is the natural parameter. So here, the natural parameter here would be rewriting c of lambda just as the natural log of lambda.